Hey, welcome. We are talking today about at least problems. Let's start by reviewing what a complement is. Talked about this a couple sections ago. The complement of an event is the opposite. That's one way to say it. So, for example, if I say there's a 55% chance of rain, then the complement is the probability of that not happening, the opposite of that. So one thing that the complement always has is like the word not in it. So whatever you want, the complement is not that. So the complement would be 45% chance that there's no rain. Okay. In fraction form, it would look like this. Say that there's a 1 out of 6 chance of an event happening. The complement would be all the other events. So if there's one way that the event can happen, then there's 5 ways that it can't happen. So it's the total minus however many possibilities were in your event to begin with. So that would be a 5/6 would be the complement of that event. Okay, picture, if we want to look at a picture of it, if this is our entire sample space, if this is the event right in here, then the complement of the event is everything else. This is the complement. So the event and the complement always add up to 1 or 100 or the total. Okay. Now, why does that matter? Let's look at a situation. We're going to take a coin and we're going to flip it 3 times. Okay, so we've got 3 events. So this is an and problem. I want to know what's the probability that I get at least 1 tail. Okay, so let's first look at the sample space. I could flip the coin and I could get all heads. I could flip the coin and get heads and 1 tail in the middle. I could get 1 tail at the end or 1 tail at the beginning. Those are all the ways that I can flip 1 tail because the order matters where that happens. I could get 2 tails and those could both happen at the beginning. They could both happen at the end or I could get a tail at the beginning and the end on either side. And I could also get all tails. So this is all the ways that I can flip 3 coins. Okay. And if I want the probability of at least 1 tail, at least means 1 or more. So that means 1 or 2 or 3 in this situation. So the options here that have at least 1 tail are these. Those all have 1. This has 2, which is more than 1. And this has 3. Okay. Now, the problem is, let's talk about just one of these events right here. Let's look at this. What's the probability that I get a head, a tail, and a head? So this is an and problem. We're going to multiply these together. Okay. And the probability of getting a head is a half. 1 out of 2 chances. There's only 2 sides to the coin. The probability of getting a tail is 1/2 and head is 1/2. So if I multiply these all together, this is going to be 1/8. Now that's only one option. Then I have to deal with the other 6 options. So you can see that this gets a little bit complicated. It's even more complicated if I flip the coin 4 times, because now my sample space is a lot larger and I have to deal with all the ways that I have at least 1 tail, which is now 1, 2, 3, or 4, a lot of different options. Okay. Now what I'd like you to notice about this is that when I say at least one, I end up circling most of the options in the sample space. In fact, specifically, there is only one situation that I don't circle, and that is where I don't get any tails. And this is where the complement's helpful. So if I want to know the probability of at least one tail, the complement of that is everything else. I don't know what I'm writing here. Sorry, tail. I'm not spelling correctly. Okay. The probability of at least one tail, the complement's going to be everything else. You have a visual of it over here. If the blue are all the options for one tail, then the yellow is the complement of it, right? So the complement picture-wise is the yellow. In English, what we'd say is the complement is no tails. Right? Because if my probability of my original question is at least one, the opposite of at least one is none. So that's an easier question to answer because there's only one option. So let's look at that. What is the probability of no tails? Well, it's three situations. And I want to flip a heads, and a heads, which is 1/2, 1/2, and 1/2, which is 1/8. Okay. Now, if I know that the yellow has a 1/8 chance, what can I say about the blue? The blue options have to add up to all the rest, right? They're complements of each other. So if the yellow is 1/8, then the complement of that, the opposite of that is the blue. So the blue has to be 7/8, all the rest, right? So that's an easy way to figure out what the blue is. So instead of looking at all of the blue options one by one and combining them, I can look at the yellow, calculate that one thing, and then find the opposite of that. So here's our general formula. If you want to find the probability of at least one event happening, the way you do that is you take 1, which represents the whole, and you subtract the probability of the complement. Now, with that formula in mind, let's look back at what we did and talk about it. What did we do? We took the complement here, which was 1/8, and then we took 1 whole minus 1/8, and that's how we came up with 7. Now we did that subtraction in our head because this is a rather easy problem, but that's the idea. Okay. So this is going to be your formula for this section. So let's do a problem with a percentage. Let's look at that. What if I say the probability that someone owns a dog is let's say 42%, 0.42, okay, of the population owns dogs. So I want to know if I choose 4 people, what's the probability that at least one person owns a dog? Okay, so a lot of options, right? One person can own a dog, the first person, the last person I picked, the third person, 2 people could own a dog, 3 people could own a dog, 4 people could own a dog. That's all at least one. So instead of dealing with all of those options, we're going to look, because it says at least, we're going to look at 1 minus the probability of the complement, which is our formula. Now, what's the complement? If I own a dog, the opposite is I don't own a dog, right? So this is going to be 1 minus the probability that no one owns a dog. So again, with the visual, we change this heads and tails to dog or no dog. And it's like every option here, somebody's going to own a dog except the one where all the people I choose don't own a dog. That's the complement. So now we just are faced with a question of what's the probability that no one I choose owns a dog. Now this becomes an and problem because I'm choosing 4 people. There's more than one event. So what's the probability that I have 4 people? So I've got 4 events here. I'm multiplying, right? Choosing those 4 people and they don't own a dog. So if there's a 42% chance that somebody owns a dog, then the way that I find how many people don't own a dog is I'm going to go 1 minus 0.42. That's going to be 0.58. This is the number of people or the percentage of people that don't own a dog, right? Because you either do or you don't own a dog. So if 42% do, then 58% don't. Okay, so if I come down here, I say, what's the probability that I pick someone right here that doesn't own a dog? 0.58, right? What about this one? Doesn't own a dog? 0.58. Doesn't own a dog? 0.58, 0.58. And then my formula tells me, now this is the situation that I don't want to happen. So I have to go 1 minus that. All right, and if you do that math, 1 minus 0.58 times itself all those times, you're going to get 0.8, let's say 87 if we round it. So there's roughly an 89% chance that you pick at least one person that owns a dog. Now think about this. If you're picking 4 people, okay, 42% of the population owns a dog. What's the chance that you get at least one person to own a dog? That's pretty high. These at least problems are usually pretty high. Okay, so again, if I want to draw a picture of it, if that's helpful, here's all the people, okay? And here is just the people that have no dogs. And everybody else has at least one. So I'm going to take the no dog situation, okay, find that probability, and then I'm going to subtract it from the whole to get all the rest. That's the idea. Okay, let's look at it in fraction form. So let's say that I tell you that 70 out of 110 people believe in UFOs. Okay, find me the probability that if I choose, let's say 3 people, that at least one of them believes in UFOs. Okay, and I'm going to say, because this is in fraction form, we'll say without replacement. So that means I'm going to choose a person and not put them back into the population. Okay, so my total, this is a dependent situation. My totals are going to decrease. My samples are going to decrease. Sample size is going to decrease. Okay, so first thing that we want to do is figure out what's my percentage of people who believe and don't believe. Okay, so if I've got 70 out of 110 people believe in UFOs, then I want to know how many don't believe. Okay, so I'm going to take 110, which is my total. I'm going to subtract 70 from it, and I'm going to get 40 out of 110 don't believe. I think that's helpful to do first to get your probabilities set up first. So those are going to be our fractions that we're working with. Now I want to choose 3 people. So there's 3 events. These are always and problems. Okay. That at least one does believe. The complement of that is that no one believes. Okay, if we want at least one to believe, then no believers is the complement. So what we're going to do is 1 minus no believers. That's our game plan. So I'm going 1 minus, and then this is going to be my no believers scenario. So first person that I draw, I want them to not believe. Okay, that's going to be 40 out of 110. The next person I draw, I also want to not believe. Now, this is like the marble problem from the other day. I'm pulling somebody out. And so my total, my sample size is going to change. So now I want 39 out of 109, right? I pulled a non-believer out, and now there's 39 non-believers left. And my total sample space went down to 109. For my third person, I now have 38 non-believers, and I have 108 in my sample space. Okay, and then I'm going to do, so this is my probability that none believe. Okay, that's poor grammar, but you can work with me. Okay, so probability of none believing. If I go 1 minus that, that's the probability that at least one believes. All right, and then if we do that, math, sorry, this is going to take me a second to type this in. A lot of fractions here. 110 times 39 out of 109 times 38 out of 108. And then I'm going to go 1 minus that. So I get 0.954. Okay. And that makes sense, right? Our original fraction has quite a few people believing in UFOs. So if I'm going to pick 3 people and at least one's going to believe, 95% sounds reasonable. Okay. So that's how you do the at least problems. It's always going to be 1 minus none. That's your formula. Okay. So if I'm at least one doing something, the way you're going to calculate it is 1 minus none of the people doing that thing, whatever we're measuring. That's it for this section, and I will see you next time.